Electropolishing, what it is, how it works, and how its effectiveness is measured. Additive manufacturing, also known as 3D printing, is being used more and more to create intricate metal pieces. This is very useful, but the problem is that these pieces are often rough because semi-melted beads get attached to the surface. And we want surfaces to be as smooth as possible because rough surfaces can reduce fatigue life, or in the case of the medical industry, it is known that bacteria attach themselves less to smooth surfaces. So when creating surgical tools or prosthetic devices, we want them to be as smooth as possible to avoid infection. So yeah, as we just talked about, additive manufacturing is able to create complex shapes, but the pieces are often rough. Traditional polishing methods don't really work on these intricate shapes because they require direct physical contact. Not only that, but the direct contact can put strain on the piece. But there is a solution. Enter electropolishing, a technique that uses electrolysis to smooth metal pieces. No direct physical contact needed. So it's able to get all those little nooks and crannies created by 3D printing. And it doesn't put strain on the piece because, again, no physical contact. Not only that, but it also minimizes abrasions, increases corrosion resistance, increases fatigue life, increases stress resistance. The surface is shinier. There are many, many benefits. And that's why electropolishing is used in a number of fields, especially where additive manufacturing is also used. There are many factors to consider when electropolishing, such as electrode distance, voltage, temperature, and many more. This makes research complex because there are so many possible combinations of variables to consider. The ideal combination is not yet known, and extensive research is required. Another important aspect to electropolishing is surface measurement. However, making surface roughness measurements is also complicated because using different profilometers with different cutoff lengths and different stylus tip sizes can lead to conflicting results even when measuring the same workpiece. So, for these reasons, it is challenging for people using different profilometers to be consistent when measuring surface roughness, which makes it even more difficult to reproduce electropolishing results. Because the electropolishing process and measure of surface roughness are so complex and have so many different parameters, it is important for researchers in this field to have a solid understanding of the procedure and measurement of electropolishing. The aim of my review paper was to provide a clear summary of the procedure of electropolishing and how surface roughness is measured, as well as to explore the different variables that influence the process. I hope you gain an understanding of how electropolishing works and of the complexities involved in optimizing its process and measuring surface roughness. So what does a typical electropolishing procedure look like? Well, the metal piece to be polished, called the workpiece, is connected to the positive terminal of a DC power supply, and the cathodes are connected to the negative terminal of this power supply. The electrodes are submerged in an electrolytic solution. The power supply is turned on, providing current through the electrodes. The workpiece acts as an anode and is positively charged, while the cathodes are negatively charged. The surface of the workpiece becomes oxidized and metal begins dissolving into the solution. These dissolved metal ions are cations. They move towards the cathodes, attracted by their negative charge. A viscous diffusion layer here, with high resistance, forms on the workpiece. It is less thick over protrusions on the metal surface and more thick in the recesses of the surface. Because of the diffusion layer's high resistance, current is most concentrated where the layer is least thick, over the protrusions. So the protrusions dissolve faster than the recessions, resulting in a more uniform surface. There are a great number of factors to consider when electropolishing. These include the type of metal being electropolished, the distance between electrodes, the nature of the electrolytic solution, and many more. Because of this great number of variables, electropolishing research can be complex. So let's explore these a little bit. It has been well established by multiple sources that increasing voltage and increasing electropolishing time are the most effective ways at reducing surface roughness. However, if electropolished for too long, black dots can start to appear on the workpiece surface. These black dots are more prone to corrosion and are a sign of over-electropolishing. Therefore, it is important to pay attention to time. Mixtures of sulfuric acid and phosphoric acid have been found by a couple of sources to be suitable for electropolishing stainless steel. Mixtures of zinc chloride and aluminum chloride make for a good solution to electropolish titanium. The addition of chromic acid has been found to not benefit the electropolishing process. Because it's expensive and toxic, it's recommended not to use it. Also, as the cations in an electrolytic solution are consumed, current density decreases, which decreases the effect of electropolishing. Therefore, the bath age, or the age of the electrolytic solution, should be taken into account when electropolishing to ensure optimal results. Higher temperatures and higher electropolishing time degrades the electrolyte bath more quickly. Multiple sources agree that bath temperature should be kept low to avoid degrading the electrolytes. Also, at high temperatures, toxic vapors can be released. So, judging from a number of different papers consulted, it is recommended that temperatures should be kept to about 30 degrees Celsius to 45 degrees Celsius. The use of a pulse current has been shown by all papers consulted to be more effective at reducing surface roughness than using a constant current. It is still unclear whether minimizing electrode distance reduces surface roughness because the papers consulted had conflicting results. So, I'm making no conclusions there. Measured surface roughness can be expressed using a number of different parameters. Ra is the mean roughness value. It's the average of the absolute values of a profile's deviation from the mean line of the roughness profile. Similarly, root mean square deviation RQ is the standard deviation from this main line. RZ is the mean roughness depth, and it's the average values of the highest peaks and the deepest valleys. RSM takes into account spacing of profile elements, and these profile elements here are XS1, XS2, etc. R delta Q is a hybrid parameter. It takes into account both height and spacing. A lower value indicates a smoother surface. Using different profilometers with different tip sizes and cutoff lengths can produce conflicting results. RA, RQ, RZ, and RSM values tend to increase as cutoff lengths increase. However, the size of the stylus tip of the profilometer is also of great importance when evaluating the roughness of a surface. A larger stylus tip, as we can see here, will not be able to penetrate as deeply into the valleys of a workpiece surface as the smaller stylus tip can. This can result in a lower RA or RQ value. Furthermore, these larger tips tend to have a higher contact force, which may scratch the peaks of a workpiece surface, and this can further result in a lower RA or RQ value. In conclusion, many challenges remain. The great number of variables involved in electropolishing makes research complex because there are so many things to consider. Many questions arise. One of mine is, if certain variable combinations are effective at reducing surface roughness of certain alloys, are they as effective at reducing the roughness of others? What I mean is, for example, if a temperature of 40 degrees Celsius, 80 volts, and 30 minutes is applied to stainless steel and is effective at reducing its roughness, can this exact same combination of variables also be applied to titanium or copper and be as effective? Also, no source consulted explored the effect of cathode material on reducing surface roughness, so that'd be interesting to know about as well. And it is still unknown whether electrode distance matters because the papers had conflicting results. However, it is important to note that different setups and even using different surface roughness measurement tools can lead to different results, which may explain these conflictions. So the answers to these questions are still unknown, and much more research is necessary to establish the answers. Measuring surface roughness, as we said, also poses a great challenge. Using different profilometers with different stylus tip sizes and different cutoff lengths can produce different values of surface roughness. Not only that, but many different parameters can be used to express this roughness, like RA, RZ, RSM, etc. The most common the most common parameter used is RA, which has shown to be highly dependent on what profilometer is used and the stylus tip size. Using the parameter R delta Q may reduce the uncertainty revolving this, as it has been found to be unaffected by cutoff length and the tool used. So it's a promising parameter to use when comparing results, though more research is needed, and it's not used by many people. RA is really the most common parameter. So because electropolishing is used in so many industries such as biomedicine, pharmaceuticals, and automation, optimizing its process would benefit many, many fields. As we said before, electropolishing smoothens the surface without compromising a piece's integrity. It minimizes abrasions. It increases corrosion resistance, fatigue resistance, and bacteria. As we said before, bacteria attach themselves less to smoother surfaces, so it's very useful for surgical tools. So, gaining a better understanding of the variables involved in electropolishing and being more consistent when measuring surface roughness is very important, because it can minimize costs and it can minimize resources. There is no doubt that electropolishing will continue to be extensively used in several fields, which is why it's so important to explore its complexities. I'd like to thank Professor Lucas Hoff at ETS for guiding Kainat and I in our project. Even if it didn't turn out the way we wanted, it was still very insightful to learn about what being in research is all about. And thank you to Julie Plante for making this entire course possible.